How's it going, everyone? And welcome to the first lecture of our course where we're actually going to be getting into the material from the textbook. I've taken this from sections 1.1 and 1.2 of your textbook, which you, of course, wouldn't know yet since you don't yet have access to the text. Just as an update on that, I've been in contact with both the bookstore along with the publisher. I actually received an email from the publisher last night where they thought they would resolve the issue for both myself and a couple other instructors that are using this text across the Alamo College District, but it did not resolve for me. So I emailed them back and let them know that. So whenever you take an engineering course, I think the first thing you want to ask, we're engineers, we want to solve problems, is what kind of problems am I actually going to be able to solve with the material that I'm learning? So when you think about statics, whatever it means to you, what kind of engineers do you actually think use this material? And on what actual problem domains? What kind of things do they apply it to? So if you want to pause and think for a minute, that's fine. But probably what immediately came to your mind is whatever discipline you're in. Since someone decided that this course should be in your program of study, it's probably important in mechanical engineering or civil engineering. Just based upon looking at the discussion board comments, it seems that's the majority of the subdisciplines that we have enrolled within our class. So certainly when you think about civil engineering, maybe you think about working on bodies or structures that are very large, like bridges or skyscrapers or highways. Maybe those of you that are on the mechanical side thought about products designed at a different scale. Maybe you thought about heavy equipment like a backhoe or something, or maybe you thought about a product that actually sits in your house, maybe something as simple as a piece of furniture. I don't think we have anyone that's interested in working on the material side of the material science side of things, but maybe you actually thought about designing a new material or something like that. And of course, these principles may not necessarily hold directly, but they could be a good model for that type of situation when the scales actually become very small. But what I'm trying to actually emphasize to you here is that the principles of statics really apply across a variety of domains and a variety of scales of problems. So really just fundamental important things for every engineer to understand, particularly those of you that are on the mechanical or civil side of things. In terms of the problems that it's asking you to solve, imagine just someone shows you something and they ask you, okay, here's the traditional type of loading conditions that this body is going to be subjected to. Is it going to move? Or here's the material that I've chosen to use in this particular product, and here's how it's traditionally loaded. Is it going to break? That's really the skill set that we're building to be able to answer those types of questions. And that's from an analysis point of view. From a design point of view, we could be asking to choose the dimensions of a body or choose the materials in order to be able to withstand a given loading condition under a traditional operating scenario. So those are the things that we're really going to be able to use this for. Probably not, to be honest with you, after a 15 or 16-week course, but for those of you that are going down along the road of mechanical design or in the civil domain, I guess in the civil domain, a lot of the problems that we're going to do in method of the various truss analysis, those do apply directly. But still, of course, in traditional mechanical design, you're traditionally going to use a finite element package in a mechanical design software suite like Inventor or something like that. So both the analysis questions and the design questions that we just asked, those are both an example of modeling. And we'll talk about what we mean by modeling here in a minute. So we want to begin by actually saying what mechanics is. And mechanics is just always a study of how a body moves when it's loaded under a force. And maybe it doesn't move at all. That's actually a subset of the problems that we're looking at in this class. And we'll define that more detailed in the next slide. But we're going to break mechanics down, or at least your text does, into how the body actually reacts when it's subjected or loaded by forces. The most simple kind of things may be something like this coffee mug that I have here. Sorry, my vocabulary. I feel like I'm pretty tired. So when I try to think of a word of what this is, tumbler, that's what I was looking for. So if I squeeze this as hard as I can, right, its shape stays the same. So I would say that's a rigid body. Under the loading conditions that I've subjected it to, which aren't just my squeeze, of course, its physical size didn't change. But if I have something like my Subway cup here, which is plastic, if I squeeze it, its physical dimensions change a little bit. And we actually call that deformation. So those two subsets of mechanics are actually different. The underlying complexity in our analysis is going to change in those two scenarios. So we're going to start with rigid body mechanics, as you always do, because it's a more simplistic way to deal with things at first. In addition, if you have a material such that if you subject it to a shearing stress, it doesn't maintain its form at all, you might recall that that's called a fluid, and fluid mechanics are an entirely different set of study that those of you on the mechanical side will definitely be taking later on. So we're starting with rigid body mechanics because in order to understand the other things, you have to understand rigid body mechanics. In addition, we can break statics down into two more subfields, and we all know this based upon the two courses that we take in sequence of mechanics. First is statics, and statics just means that a body is not accelerating Remember that acceleration, by definition, is the time rate of change of the velocity. So that doesn't necessarily mean that it's stationary. It just means that it's maintaining it at a constant speed, which most often in our cases will be zero. And then we will look at in the next case, and I should have non-zero acceleration here. I will fix that. Sorry, you got to watch it in real time. Dynamics is nothing more than the study of bodies that are accelerating. And we'll see when we get to the Newton's law portion of this lecture that what that means is that there's some type of unbalanced or resultant force acting on the body. So why do we consider statics as a separate discipline? Well, ideally, if everything's working correctly, a lot of things around us aren't moving. Structures are designed to be at rest. So it's important to look at that as a subset of rigid body mechanics first. In addition, of course, the math is going to be easier. So it's a good place to start. So when you think about what engineering is and how this kind of came about from a historical point of view, we're data-oriented people, right? Show me the data. Just don't give me your opinion. So how do you get data? Well, to get data, you need physical instrumentation to be able to take measurements, or you need kind of phenomenon around you to be able to observe what's going on. So statics is a really old discipline dating back before Christ, about 2,500 years, because a lot of the physical tools that allow us to observe principles of statics, like the idea of torque in the form of a lever, just date back to that old of time. In contrast, when you're talking about actually measuring dynamic quantities accurately, right, things that are actually accelerating or changing their speed, in order to be able to measure speed precisely, we need devices to be able to measure time precisely. So the principles of dynamics are much newer from a historical perspective, of course, still very old, thinking back to Isaac Newton being hit in the head with an apple, but compared to statics, they're much newer. So one thing that the book goes over that I just want to review very quickly is when we're doing problems in statics, we're concerned with four fundamental physical quantities. We need length in order to be able to describe the physical dimensions of bodies along with their separations. We will need time and dynamics, at least, in order to be able to describe your book. Talks about how momentum is accumulating, but momentum, as you'll see when we get to that point in the course, if you stick with us, with dynamics, is inherently related to this ideal of speed changing, which basically means that something is accelerating. In addition, we need to describe how, for a given loading condition, how much resistance or inertia there is to motion, and that property is actually the mass of an object. So, of course, we remember mass as being nothing more than a measure of how much matter is in an actual body. And force is the fundamental quantity that's going to cause this all to happen. It's what the quantity that we will describe, that a quantity rather that describes how bodies interact with one another. So we can have direct contact forces. I can take this hand and interact with this hand and push, and that's a contact force. And of course, I can have forces acting at a distance as well. And I could see that if I raise my phone or any object with mass and I just let it go, it would be attracted to the center of the earth, even though there is no physical contact between those two entities, in that case, my phone and the earth. Now, the cool thing about force, or maybe if you like math, it's a cool thing, but if not, we have to deal with it anyways, versus those three other fundamental quantities, is that it's not fully described by a single number, which is known as a scalar. In order to fully describe it, you need to specify both the magnitude along with the direction, and more particularly, in addition to just being a vector, which is what that means in terms of describing magnitude and direction, in order, in most cases, when we actually get with non-concurrent forces and deal with rigid bodies, we'll also have to be specific about its point of application on a body. So looking a little bit more at fundamental content, and going back to that ideal on slide 1 that I talked about with modeling, when we're dealing in statics, if we're going to take a body, like something like this coffee cup, and we can ignore its physical dimensions, and we can only talk about its mass. In that case, what we're doing is we're actually applying a particle model. And one of the key concepts, and we'll define this in more detail as we get into both statics and dynamics, is that if you can describe something using a particle model, by and large, you're only talking about translational motion. You're not actually considering rotation. And in the case of statics, we're not talking about motion at all. So really what we're going to find is that we can employ particle models when we don't have to think about torques counterbalancing one another in order for an object to stay stationary. So why would we ever use a particle model? Well, as engineers, we are always getting paid to come up with the simplest solution that does the job. And if we can ignore something like the physical dimensions of a body, it's just going to make the underlying model easier, as we'll see as we move from chapters 2 and 3 to chapter 4 in the text. So one of the things that I wanted to hammer home here is when we're talking about a particle model, we're ignoring the physical size, but we're considering its mass. But it doesn't necessarily mean that if we're modeling an object as a particle that we're saying it's small. It's just saying that in this particular scenario for the loading condition or what we're interested in analyzing, that we don't need to consider the physical dimensions in order to get to the result that we need. So rigid body, we're just going to use that for any body that when it's subjected to loads, it doesn't deform at all, it doesn't change its shape, or if it changes its shape, it's ever so slightly and it doesn't actually affect the analysis. And that's what it means by practical deformations can be ignored there in your text. So concentrated force, what I mean by that, well, you can't really see my coffee cup actually sitting on my laptop here, but at which points on the bottom of that coffee cup is my actual laptop exerting a force on the mug here in order to counterbalance its weight? Is it right in the middle? Is it right on the edge? Well, physically, that contact is distributed over some surface area. So whenever you have a contact force that's distributed over a finite area, but you're going to model it as just being applied at a single point, the book will refer to that as a concentrated force. So let's actually look at a couple of example problems to make sure that everyone's on the same page here. So here we have a wheel of a railroad car that is on a track, and we're depicted here to the right. The textbook authors have shown a white arrow to represent the contact force between the rail and the wheel. Why is the force drawn as an arrow? Well, remember, a force is defined by three things in terms of the physical quantities that we discussed: a magnitude and direction, meaning it's a vector, and a point of application. And in general, in physics, when we see arrows, they are natural kind of tools to use to describe vector quantities, because you can vary their length to talk about magnitude, and you can vary their orientation relative to some reference axis to change their direction. So drawn as an arrow because forces are vector quantities. And assuming the wheel is made of steel, why would rigid body analysis assumptions likely be valid? Well, when you think about it, there's lots of different loading going on to that wheel, assuming that it's sitting stationary. But by and large, we can assume that if it's just the weight of the wheel itself, along with some other weights that it may be supporting, that under that loading condition, if it's made of steel, it's not going to deform. So if its physical shape doesn't change, then rigid body analysis is good. Some other example problems, just to hit some points home. When you're modeling a body as a particle, what physical quantities are considered and what are ignored? Well, in a particle model, you consider the mass, but you ignore the physical dimensions, and it doesn't necessarily mean that it's small. And rigid body mechanics, just to go over that again, that just means that under a given loading condition, a body is not deforming to any reasonable amount. It's not changing its shape to an amount that would actually influence the results of our analysis. So hopefully that made sense to you, and I'll see you all in the next learning module.